Today we're going to build polynomial functions, and to start off with our notes, we are going to start off with a little bit of a review by writing the following cubic polynomial equation in its factored form by grouping. We haven't factored by grouping for a while, but that'll be good to get that skill back again. And remember, what we do is we divide our polynomial into two groups, and we factor the greatest common factor from each group. So we're going to factor out an x squared, and when we factor out an x squared, we had 3 x's, we took out 2, we got 1. And we had 2 x's, we took them both out. So we got x squared times x plus 2. Be careful here because there's a minus in front of that 9x. But our greatest common factor from that second group then is going to be minus 9 or negative 9. And negative 9x divided by negative 9 is x. Negative 18 divided by negative 9 is 2. And then what we have here is we've got an x plus 2 in both groups. And then we have an x squared minus 9. The thing is, if you're really looking closely at this, you would raise your hand and say, we're not done factoring. Because we can factor a little bit more. The x squared minus 9 can be broken down when we take the square root of x squared, which is x, and take the square root of 9, which is 3. Difference between two squares, different signs. And now it's completely factored. The thing is, if we can get the function completely factored, then we can come up with our roots. And for some of you, you know what the roots are right now, and you don't have to show all the work that I'm going to show. But if worst comes to worst, we're taking x plus 2, one of our factors, setting it equal to 0, x minus 3, setting it equal to 0, and x plus 3, and setting it equal to 0. And when we subtract 2 from both sides, we get x equals negative 2. When we add 3 to both sides, we get x equals 3. When we subtract 3 from both sides, we get x equals negative 3. And those are our 3 roots, our x-intercepts, our zeros of the function, as the wording says. Now the thing is, I am not going to type this into the calculator, but if n behavior is causing you a little bit of trouble, then type it in the calculator and look at your n behavior. But the first thing that I notice on this particular problem is that our leading coefficient, which I'm going to abbreviate as LC, leading coefficient, is a positive value. And what we have learned over the past week and a half or so is that when the leading coefficient is positive, the graph finishes going towards positive infinity. So to the right, as x approaches positive infinity, then our y is going to approach positive infinity. The other thing that I hope that we as Algebra 2 teachers have stressed is that because this function is a cubic, and therefore odd, to the third power is an odd number, our n behaviors go in opposite directions. So if we know this is positive infinity, this one must be negative infinity. Again, if that doesn't make sense to you, type it into your calculator and look. What happens as we go towards the left on our graph, as we go towards negative infinity? What happens as we go towards the right on our graph, towards positive infinity? Finally, as we look at this problem, again, here is something else that we haven't talked about for quite a while, but the question is, what is the y-intercept? And the thing is, an ordered pair of a y-intercept is 0 something, and that 0 is an x value. So what we can do is we can go back into our function, and we can say, well, 0 cubed plus 2 times 0 squared minus 9 times 0 minus 18. And what happens is 0 cubed is 0, and 2 times 0 squared is 0, and 9 times 0 is 0. Our y-intercept is the constant of our polynomial function, which is 0, negative 18. Again, something else that you might be able to find in your table screen of your calculator. Finally, we've talked about the fact that this is a cubic function. Cubic function is to the third power. How many maximum turning points can we have then? Because it's a cubic function. 2. Our turning points are 1 less than the degree of the function. Our degree is 3, so our turning points are 2. Problem number 2, or 1 actually, because the first one was review. The graph below is a quadratic polynomial. Use the information from the graph to write the possible function rule for f of x. Express this equation in equivalent factored form and standard form. And then to check your work, which is something I'm not going to do today, you can type our answers into the calculator and they should match the picture on the screen. But if we take a look over here at this, first of all, it says state the intercepts. Well, our intercepts are here and here. 1 and -3. Don't put parentheses around there. It's not an ordered pair. Those are our 2 x-intercepts, where the graph crosses the x-axis. And on your paper here, you might want to do what I just did, which is put a line there. Because now what we want to do is we want to come up with the factors of it. And some of you are going to need to do this step, and some of you are not going to need to do this step. But what we have here is we have x equals 1, and we have x equals -3. To get this back in factored form, we're working backwards. We subtract 1 from both sides, and we get x minus 1. We add 3 to both sides, and we get x plus 3. Therefore, in factored form, we can say this is x minus 1 times x plus 3. There's the factored form. Standard form means that we need to multiply this out. So we're going to use double distributive property. We're going to FOIL however your Algebra 1 teacher taught you, but here, 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 and here is what we're going to be doing. And on my paper, I wrote right beside standard form, I did the work. X times x is x squared. X times 3 is 3x. -1 times x, and -1 times +3 is -3. And then to write it in standard form here, we can combine our like terms, the 3x minus the 1x. We get x squared plus 2x minus 3. Again, the checking mechanism, as some of you are still writing down, is type in x minus 1 times x plus 3 in the calculator. Do you get that picture to the left? Or type in x squared plus 2x minus 3 in the calculator. Do you get that picture to the left? Problem number 2. Consider the function q of x equals -x times x minus 3 times 2x plus 5. What we want to start off with here is we want to figure out, well, what are the zeros, the roots, the x-intercepts of the function? And some of you need to do this, and some of you don't need to do this. So, gotta write it correctly. X minus 3 and 2x plus 5. So when we solve this here, we can divide both sides by -1. We get x equals 0. We can add 3 to both sides. We get x equals 3. We can subtract 5 from both sides. We get 2x equals -5. And divide both sides by 2. So x equals -5/2. Those are our zeros, our roots of the function. And now what it says here on part 2 is part B, it says write an equation in standard form. Well, you have enough space on your paper. I don't have enough space here on my screen. I'm going to start up here. -x times x minus 3 times 2x plus 5. And what we're going to do is we're going to multiply these 3 parts together. But when we start, I'm going to start by multiplying those 2 together. And that's just going to be a distributive property here. And -x times x is -x squared. Negative x times negative 3 is positive 3x. And then we're going to multiply by 2x plus 5. And that's going to be our FOIL process, or our double distributive property. Negative x squared times 2x is negative 2x cubed. Negative x squared times 5 is negative 5x squared. 3x times 2x is 6x squared. And 3x times 5 is 15x. First, outer, inner, last, if you're using that method. But now to finish, I'm going to infringe on my space. You have enough space on your paper. I don't have enough space on mine. But when we combine like terms here, we end up with negative 2x cubed plus x squared. Negative 5 plus 6, combining our like terms. Negative 5 plus 6 is 1, plus the 15x. That's our equation in standard form. And since I'm infringing on the space in D here, question D says, what is the maximum number of turning points of this function? Well, our function is a cubic polynomial. It's to the third power. So what's the most number of turning points we can have? 1 less than the degree. So you have enough space on yours. I just didn't have enough space on mine. But I gave away then part C here because it says classified as polynomial. Again, what we're looking at is we're looking at this 3 here, which tells us that it's cubic. In terms of end behavior, even though I'm not spending the time to type it in my calculator, you could spend the time to type it in your calculator if you do not know the answer to this one. But once again, when we look at this, I like to look at it from the perspective of the leading coefficient. And the leading coefficient in this particular problem is negative. And in fact, how could we have predicted the end behavior? That's what I'm doing. I'm predicting the end behavior because the x is negative in the question. It says, how can you predict the end behavior? The x is negative. So that tells me that the leading coefficient is negative. So when we come over here, we know that to the far right, since our leading coefficient is negative, our graph is going to be going downward towards negative infinity. It is a cubic function, which is an odd value. And that means that our end behaviors go in opposite directions. So this is going to be positive infinity here. Nothing wrong with looking at the picture on your calculator to determine what the end behavior of the function is. Turning over our paper, it says the graph at the right is a polynomial c of x. And first of all, take a moment and look and decide how many turning points are we going to have. Well, we have 1, we have 2, we have 3. So the graph at the right has 3 turning points. So this time we're given turning points. So what's our degree? And you should be going 4 because our turning points are 1 less than the degree. So we have to add 1 to 3 to get our degree. This graph has an intercept here, an intercept there, and an intercept here. It has, therefore, 3 unique x-intercepts. And those values that we just marked on our graph are -2 and 0 and 3. The leading coefficient. If we look to the right on this graph, far right, our graph is going downward towards negative infinity. That means that the leading coefficient of this polynomial is going to be negative. And so now that we know this information here, eventually what I've got to do is I want to make sure that I'm going to write down a negative come from there, just so I don't forget to put it in later. Because now what it says use the information from the graph above to write a possible rule for C of x. Well, once again, what I'm going to do is I'm going to take our three intercepts, and they are x equals -2, and x equals 0, and x equals 3. And then what's going to happen, and some of you don't even need to write this step, but I'm going to move the 2 over here. And we get x plus 2. And I'm going to subtract the 0, although you could add the 0. And the thing is, do we even really need to write down the 0? And we don't. But we can subtract the 3 from both sides. And we get x minus 3. So in one format here, what's going to happen is we're going to get x plus 2, and then x, because we don't really need to write the 0, and x minus 3. I just would like to say that in general, I tend to like to write the x out front. So up to you, it's not going to make any difference when we multiply these together. But there's an alternative way to write the function. The thing is, we need to go back and look at our picture a little bit more, because at the intercept of -2, we cross the x-axis. And because we cross the x-axis, we're going to have a multiplicity of 1 on that vector. When we go to our root of 0, we have a U-shaped curve, and in fact we touch the x-axis at 0. When we touch, we're going to have an even multiplicity, and a U-shaped curve is better known as a quadratic. Our multiplicity on x is 2. So when we get over here to 3, once again we cross, and cross is going to be to the first power. So as we finish this here, let me put it in also on that bottom one. It's -x squared times x plus 2 times x minus 3. We don't necessarily have to write to the first power. But now that we've got that, we're going to take those values here and we're going to multiply them together. So once again, our function is -x squared times x plus 2 times x minus 3. Multiply these first two together with the distributive property, get an answer, and then multiply by this last one. So we're going to end up with -x cubed minus 2x squared. We multiply those together. So we're taking our answer now, we're going to multiply it by x minus 3. So -x cubed times x is -x to the 4th. -x cubed times -3 is positive 3x cubed. -2x squared times x is -2x cubed. And -2x squared times -3 is positive 6x squared. We have like terms here and here. And ultimately what we end up with is we end up with -x to the 4th plus x cubed. 3 minus 2 is 1. plus 6x squared. And if I want to get technical, and I don't need to be super technical, but I will put in function name. So there's our function. Again, you could type this into your calculator, and your equation should give you a picture that looks like the picture that's given to us. Last example. Given the following roots, build a polynomial in factored form with integer coefficients. Well, first of all, this looks a little bit weird, but all that it means is x equals 2/3. X equals -5. X equals +5. And x equals +4. The thing is, it says, given the following roots, build a polynomial in factored form with integer coefficients. Integer to some people is a huge relief because that means no fractions. But let's put it in the proper format here. Let's put it in a factored form and then we'll fix the fraction. So what we do to put it in factored form is we're going to subtract 2/3 from both sides. We get x minus 2/3. And we add the 5 to both sides. We get x plus 5. And we subtract 5 from both sides. And we get x minus 5. And we subtract 4 from both sides. We get x minus 4. Once again, in standard form, we don't want fractions in there. So a while ago, we used to have a method that we used for factoring called slide divide bottoms up. And while it was good, it also had some flaws in it, so we don't use it anymore. But the bottoms up part is still good. What we can do is we can take our fraction here. And what we're going to do is we're going to move the 3 up. So the 3 is going to go up, and this is going to turn into then 3x minus 2. No more fraction. So I'm going to say bottoms up, and some of your other teachers may as well. But then we can put it in factored form. And it is 3x minus 2 times x plus 5 times x minus 5 times x minus 4. And I should have probably done it first. But what's the degree of this function? If you think about it, we've got x equals 2/3, there's one answer. X equals -5, there's a second answer. X equals +5, there's a third answer. And x equals 4, there's a fourth answer. 4 answers means fourth degree. How many turning points do we have if we have fourth degree? And one question that's not asked on here is, what do we call a fourth degree polynomial? It's called a fourth degree. Just as a refresher, I don't want us to forget these different terminologies. But don't try to get this last one written down here. And then speaking of degrees, before we even do any work, what is our degree on this particular problem? It's 5. 1 answer, 2 answers, 3 answers, 4 answers, 5 answers. So if our degree is 5, how many turning points? 4. And this is another format here of writing the answers or the zeros or the roots of the solution. This is simply x equals -5. X equals 1/2. X equals -4/3. X equals 1. And x equals 0. A little bit. But now, we can put it back on the form, but also, let me remind you, no fractions. So we're going to add 5 to both sides. Again, some of you don't have to show me that step. Some of you can go directly to it. Subtract the 1/2 from both sides. We get x minus 1/2. Add the 4/3 to both sides. We get x equals 4/3. Subtract 1 from both sides. Oh, did it twice here. Didn't write it. So this is x plus 4/3. This is x minus 1. Again, with the minus 0 or the plus 0, it's not going to make any difference. We don't really need to write the 0, that actual number, down. Lastly, with respect to our fractions here, bottoms up, move the 2 up, and this becomes 2x minus 1. Bottoms up, move the 3 up, and this becomes 3x plus 4. And then we can finish writing our polynomial in factor form. It's f of x equals x plus 5 times 2x minus 1 times 3x plus 4 times x minus 1 times x. And just as an aside, I would write the x first, but clearly you don't have to.